Okay, welcome all to the webinar. We are still waiting like a few minutes before starting that everybody's getting here. Welcome everyone to the webinar. We will shortly start within like 1 minute, so we still wait like the last minute arrivals to this webinar, and then we start. I can tell about the practical things. So this is a live event, and it actually means that you can ask questions. So if you have any questions about the topic, you can type them in the chat. So there's a raise hand button in your webinar tools, and you can press that and type the questions. I try to answer as many as possible, but if it's we have a lot of questions, we have Isak from Sweden to also answer the questions, so he can also answer. And if there's any like questions which remains unanswered, we try to answer everyone after the webinar. So the questions will be recorded, and that's why we can answer those afterwards. So no panic if I don't have time to answer every possible question. So that basically we are planning this to be like 45-minute event, so that is roughly the duration. We still wait like a few minutes to last ones come in. But anyway, welcome. It's nice to have so many people this morning to come to our webinar. And this is a part of webinar series we will host in StruSoft about all the technical things related to software, and also like practical design of steel and concrete and timber. So if you have any wishes about future topics, what we might want to cover in these webinars, you can definitely contact me or Isak or anyone from StruSoft, and we take your wishes. I think we can start. So roughly the agenda today is that we will try to give you an overview of the whole stability process, how you should handle the stability calculations in Eurocode 3, and also a few tips about practical steel design, what I have like gathered in 15 years of designing steels, and tips about how you apply the total stability checks in your steel model, and how you, well, the details of the stability, like local stability and local buckling, they are not part of this presentation. It's a very complex topic, and it's left out by intentionally that the topic does not get too complex. So that is like the overview of the whole stability analysis according to the Eurocode is the thing today. And for the latest incomers in the webinar, we have a possibility to type some questions. So please use that possibility if you have any questions about things we handle today. So first few words about what we are and what we are selling. So our product is called FEM-Design, and it's a very versatile and easy to use and intuitive design software for structural analysis, and it's what we are usually really famous for. We are develop the software with the clients, and usually we offer this product as a service. So we we are close to clients, we coach them, we teach them, and ask the problems and solve the problems together. So that is like our specialty. And today we are discussing about steel design and our steel joints design, but mostly we are focusing on the Eurocode and how you should do it. So anything you hear today, you can also apply to the other software. And this is the probably the most confusing, or at least what I have thought the client's most confusing dialogue in our software. So it's located here, and the program will ask you that how you would design this single element. This same thing is handled in any other software, a bit different. But anyway, this is the basic question, which is hard to explain. So the options are like ignore second order analysis, consider second order analysis, or then the third option is the second order internal forces plus the first order design. So this is like confusing for most of the users, at least if you are beginning to use the software or beginning to use the Eurocode in general. So what is all this mean? And I hope I can answer this question during this webinar. So what these selections in this menu will mean. And I have always described that the Eurocode is like a process. So it's a process about selecting of structural systems, and then it's a process of doing some analysis method choices and then design method choices. And the full process of this Eurocode is here. So in the first glance, this seems to be like overwhelming and really complex chart. What's going on here? It's a really complex, and the problem in Eurocode, it's not stated very clearly in the text. It's only like text form, and this is the actual flow chart what I have done to explain the whole process, what stability should be handled in Eurocode. In top left corner, we have like structural system choices, which will affect the connection stiffness and the stiffness of parts. And then we calculate the critical loading of the structure, like the global buckling mode. And then we proceed with the second order or first order analysis. And then we design some parts, and also in design phase, we need some take into account how the total stability analysis of the whole frame is done. And that is the thing which been chosen, that menu what I show you. So let's go deep dive little bit closer to this process. And these are the like three main areas. The green one is the structural system choices, and then the red one is like how you done your analysis, and the blue one is how you do your like design of the whole parts of your design. And usually the problem is that this green part, this is the most difficult one. This will make you like many, even 10 years to master. And the green one, okay, the red one, that's like how you analyze your structure, and that is easy to learn. It can be understood in few years that what is nonlinear analysis, what is linear buckling analysis, nonlinear buckling analysis, and so on. And the blue one, like you design your parts, usually like design checks, they are really easy to do in software. You just click the element, and the software will give you utilization. You just give you like buckling lengths or lateral buckling lengths, and it's like straightforward to do. But the most knowledge is usually in the beginning of process. That's where usually, and it's a most difficult thing to learn. So we give you now a few tips about these structural system choices. And usually if you select these like really well, your structural system, it's easy to design your steel structure. So usually if you stick to these limits, like for beams, your span length to the height of the beam ratio is between 20 and 30, and the spans are below 20. Your design is like reasonable. It's usually easy to design. The connections are easy to design. Forces and bracings are not to be like too big. And the roof beams, it's about the same. And if you go like to the trusses, you should usually consider something like that. If the span is like 12 meters, your height should be like 1.2 meters or 1 meter. And if you leave it like there, the area, usually your design is really conservative. It's the internal forces of your elements does not grow really high, and the design of connections are easy. One specialty is these portal frames, and they can be really efficient. It takes into account both like tension flange and compression flanges of steel frames, and it uses both flanges really effectively. That's why they have a so high span to depth ratio, those portal frames. That's an efficient way to use steel. And the space truss is the same. It's you have a lot of elements in the small space, so you can kind of get more slender structures. So if you stick to these rules, it's easy to design your like truss connections and all the stiffening elements of your structure. Of course, these are not like fully fixed rules. So if you don't obey these, okay, you can go along, but you eventually will run to some problems later. Then I have listed few problems to avoid in steel design. These are just not the like complete list. Oh, we have a question there. Span height, of course, if you have a really high loading, it's about the question about that. Is this like this recommendation like load related? Absolutely, but anyways, mostly it's so that you select this something like related to this span to depth ratio, and then you just do the buffer elements. Of course, if you have really high loading, you should consider to reduce these limits a little bit. So it's mostly like it's not like a load related, but partly in cases of really low loads or really high loads, you can go below or over these limits if you want. But these are like for typical structures, you should obey these. And always if you have a possibility to do like multi-span beams, the steel is used much more efficient that way if you compare to the single span. So if you do like fixed connections to the columns, or you do beams over the columns and do the connection elsewhere, there is a more efficient way to do steel. Then your diagonal angles, it's a truss or is it a stiffening system, you do not want to go below 30 degrees. Your connection forces will go like really high, and design of connections becomes really difficult. And the comfort criterion like vibration is also important. So this is like the rough hand calculation of the eigenfrequency of the floor. So make it that it should be like even if above 10 hertz is good selection here. Then other problems, okay, pre-camber, if you have like welded beams, you can pre-camber them, but do not go more than 70% of the dead loads. And the reason is that you should, if you design your connections, you design them as by pinned assumption. And in the reality, nothing is pinned, so you have a friction. And if you put too much pre-camber, it can be so that the beam is bent upwards when you execute your structure. So that's why the pre-camber cannot be too high. Prefer ductile connections. This is out of the scope of this webinar, but it's a good idea to prefer the connections which are the stresses are divided evenly. Then thermal loads, which is usually forgotten in structures, but in some cases they have really high impact on the some local stresses can rise for thermal loads, and it's for steel it's important. And imposed loads like imposed deformation as foundations, they are seldom done in steel structures, but some cases they should be done. And when you're designing your non-sway columns, it means that it's supported column and it's just compression. It should be always designed to the much safe side, because the problem is that there's eccentricities and things like that, which usually you haven't taken into account. And also leave some safety margin. It's safe. If you don't know what you're doing or bit insecure, it doesn't hurt to leave some safety margin. And usually the worst mistake is in steel, and especially in steel, is that I don't even think about it. So it means that there's some stability phenomenon in the structure you don't even have thought about. And also the responsibility boundaries in projects, they are hard. Usually the problems are there. Somebody gives you loading, and then the loading does not include everything, or then somebody else is designing foundations and like steel, and somebody else is designing like the steel. Then there's always risk on those responsibility boundaries. Okay, and this is a good idea to check also the slenderness of steel elements. This is not in Eurocode, but it's in the old dimensioning standards. There's a recommendations to do some slenderness checks of elements, and the slenderness is simply, it's called alpha, and it's ratio between the span length and the stiffness of the element, or the buckling length in here. So if you stick to these limits, you do not end up in problems. Especially if you have like really slender braces and columns, the problem is that they are really sensitive to lateral loads and vibrations and cyclic loading. So it's in all dimensioning standards there's a slenderness limits, but in Eurocode there's not so. But anyway, if you stick to these limits, it's always a good idea to then you have avoided many problems. Then there's also a thing to select the right analysis model. So usually those steels, they are calculated with the beam ideology, but it's a problem here is that the beams doesn't work every time. Beams will work if it's really long, and if it's like medium thickness beam, let's say it's like 3 meters long and the height is like 1 meter, then it works if you take into account the shear deformation. But if you go like really low, like cantilevers, or like the beam is like 1 meter long and 1 meter high, it's no longer a beam. It should use shell model or solid model, like in here. This is not like a really short beam, but anyway, this shows how shell models will work. And in our software, it's always possible to convert beams to the shells to analyze those shorter span to depth ratios. So the beam model is not always the right model in steel, and the same applies to the concrete. But it's good to know that if the beam is really short, the beam analogy will not give you the right results. Okay, then is the first example, the eccentricities in steel structures. The most common way is to model those steel structures with like the point to point, like without any eccentricities, and it's not always the right solution. So if you have any doubt that should I use eccentricity in my steel frame, it's better to use them. It does not hurt to put them in the model. And the problem is always when you have a low height to length trusses, like really slender trusses and slender frames, then those eccentricities will give you lots higher utilization, and they give you problems. So if you stick to the conservative design rules of the trusses and frames, then probably the eccentricities will not cause you problems. But with the high slenderness frames, the eccentricity will be more important. There's a question. If the beam model is selected, is it possible to consider the local buckling in FEM-Design? We will take into account the local buckling, the shear buckling, and of course the cross-section classification is taken into account, the buckling in lengthwise forces. But we don't have any like local force checks in FEM-Design. But it's easy to also put some stiffness in the location of the high loads. Also, non-sway columns, it's important to put those eccentricities there, because usually they are like centrally loaded. And we have a tool called point connection, so I can show you how it works. So that is the best way to model these. So let's go here. So here is like two identical frames of steel structure, and on the right side we don't have any eccentricities, so this is like the standard way to model those steel frames. And on the left side we have a model with the eccentricities. So if you look the field model here, let's go to the structure to see better. We can have a connection here, and the connection have a eccentricity, so they are not like centrally connected. And if we design like this is like a braced frame, so it cannot move. So if you go to the steel design and then we design those elements here, we have a much different utilization of the models depending on do we have a eccentricities or not. So let's look how they deviate. Like for instance here, if we include the even little bit of eccentricity of the column, it's much higher in this model. So the utilization is like 108% here, and if you go to this model, it's 62. So actually the connection eccentricity is really important, and same applies to the truss, because in this top joint we have a lot of eccentricity here, and it's not taken into account if you model it like this, that the beam is connected to the center line. So if you have any doubts, it's always safe side to use those eccentricities on your model. And the eccentricities should be taken into account in the connection design and also in the overall analysis. By default, our software will design all the connection with the eccentricities. But if you want to take them into account in the global analysis, it's better to model them by the point connection tool. So it's I forgot to show you the tool, but it's here. So you can do any kind of connection with this one. It's easy to just select one element and the other element and do the point connection, pinned or rigid point connection between them. And here are the examples of real eccentricities in steel. So usually, if you have really tight bolts, they don't cause any problems. But then again, have you considered the tightening torque of bolts and check the slip resistances of your bolts? So it's always safe side estimate to design your columns with the eccentricities taken into account. Then we go to the connection stiffness. So this is the next part. So the problem is that when we're doing the total stability check, the connection stiffness has to be taken into account because we have a correlation between the critical loading and the connection stiffness. Joints can be classified like at least 3 ways in Eurocode. We have a capacity classification, so it means that if the connection is stronger than beam or weaker than a beam. Then we have a ductility classification, so it will tell you the rotational capacity. And then we have a stiffness classification. And the problem with the stiffness classification is that it's always compared to the beam or column, connected beam or connected column stiffness. So it means that if the column is really slender, you need weaker connections to make the connection like classified as rigid. So here is the Eurocode classification by rigidity. So the problem is here that we have a semi-rigid connections. We can have rigid connections. If you have a like really slender column, the connection does not have to be so beefy to be classified as rigid. And flexible is easy if you're designing like pinned connection. Well, it's a pin if it has just have enough rotational capacity to take those deformations. And usually the problematic area are these semi-rigid joints. And the other problem is that it's not even one like linear spring coefficient of the connection. We have this factor mu in the connection stiffness formula, and this will take into account the utilization of the joint. And in Eurocode, those joints are calculated by like with the plastic theory into account. So it calculates in a plastic fashion. So if we calculate the capacity according to the Eurocode, it will go over the plastic limit, and it means that those connection stiffnesses will be reduced when the utilization is high. So if you calculate the total stability of the frames and the utilization of your joints is really high, you run into problems. Also, the utilization has to be taken into account according to the Eurocode. There's a question. Is the eccentricity in your example modeled by making the beam actual length and then making the point connect to the center of column? Yeah, that's what is done here. Actually, the beam is not like actual length. The beam is modeled as length to the joint bolts center of gravity. So it's like the best way to do it. That the beam will continue to the center of gravity of all the bolts, and there you do your connection to the columns. And with the eccentricity, we will model the situation where there's the bolts have been slipped or they are not pre-tensioned correctly. So that is what we want to model there. So from bolt center line, bolt group center line to the center line of column is a good choice to do the eccentricity. Okay, we continue. So the problem is this mu, but this is usually handled by software. So that is good thing, or depending on the software. But you have to know what your software is capable and what is not capable of. So if you calculate like total stability of your steel frame, here's our example building, and we want to calculate like sway buckling of this main frame here of the building or structure. We go to the steel design, and there's we have a tool called connection design, and under the connection design we have a tool called stiffness. And if we check any joint in the model and then we check the stiffness again, here we can see that what is the actual stiffness of the connection. And we can also see the utilization. So if the utilization goes like 80% or 90%, then we have to reduce the stiffness of the connection in the global model. And here we can select, the user can select, should we include the connection stiffness in the global analysis of the frame. And usually the practical option is this, that we use the connection stiffness with the highest utilization. If the utilization in some combinations go like to the 90%, we have to reduce this final connection stiffness in model. We have a question there. Or do we? I don't see any question. Okay, Isak, can you answer the question if you find it? I don't see any questions there, but maybe there were some. But anyway, it's good to understand when we are calculating like the total stability of the building. We have to design our connections really stiff, make certain that they are like stiffer than the column or classified as a rigid connection, or if they are not, then we have to take those connection stiffness into account. And in our software, it's easy. If you have a connection design, you just calculate this, use this stiffness button to calculate the exact stiffness. And always the good option is to do such connections which will classified as a rigid or classified as a pinned. So that's like safe as some of the really neat way to handle your frames and design of frames. Okay, now we know our connection stiffnesses, and then we go. Oh, do we have another question? How did you come to the connection initial stiffness in equal to the second stiffness, or did I misunderstood? The initial stiffness is calculated based on the component stiffness, and it's maybe the utilization in the connection was so low that it does not need to be taken into account. So if the utilization is really high, then those two, like the final stiffness and like initial stiffness, they are like identical. But if the utilization will come to higher, they will deviate. Okay, then we have to calculate this green in this green box, the alpha critical, and alpha critical means that what is the factor we have to multiply all the loads to cause elastic instability in the structure. And based on the alpha critical, we do some choices. So if the alpha critical is way above 3, we can do linear analysis, but only if it's like regular building, and then we have to increase the like wind loads and soil pressures and all the lateral loads in the frame. So we have this load increment factor. But let's discuss first about the alpha critical. So the alpha critical means that what is the multiplication factor for all the loads in the case. And in Eurocode it's stated that if it's over 15 or 10, you can do a linear analysis, and if it's below 10, then you have to do something. And usually it's this, that you have to increase the lateral loads in your model. And this is the easiest done in the load combination factors. That's the most easiest way to put it there. If you have like alpha critical, which is like below 10, let's say it's like 8, so the column critical loading is like 8 times the current loading. It means that we have to increase the lateral loads. And for simple frames or multi-story simple frames, we can use this approximation that we can still use the linear analysis, but we have to increase the lateral loads by this factor. If it's like really complex structure, then it's no other option to only use second order analysis to analyze your frame. But if it's a simple frame, you can use this factor to modify, provided that the alpha critical is above 3. If it goes below 3, you always have to do second order analysis. So that is actually what's going on. And there's an option to calculate this alpha critical with this approximation formula, like taking the horizontal and vertical loads and the height and the deviation of structure in ULS. And with this formula, we get the alpha critical of 4.5. So it's a really close to the like exact solution what we find by eigenvalue analysis of our model. So we go here and check that what is the stability analysis, and here is the critical loading, and it's this is the lowest loading 5.5, and it will look like this. I know actually I can take this color palette solution. It's easier to see, and let's put on the deformations. Maybe with like, okay, here's the. So the actual factor is a bit higher. It's 5.5, and with this simple approximation, we get only like 4.5. And the difference is because we have other stiffening elements in the frame, not just like the columns. And by the way, if you look this column now, the stiffness of the connections have been taken into account. So that's why when we calculate alpha critical, it's important to know your connection stiffness, especially if your connection stiffness is not like ultimately rigid. Okay, let's assume that now we know the alpha critical of Jackson, and in this case it's a 4.5. So it's above 3, and in special cases, if it's like regular building, we can just increase the wind loads. So we come to this part here. So alpha critical was above 3, so we can use this factor to increase the wind loads. So it will give you like 1.4, 1.3 to increase the wind loads and increase all the other lateral loads what we have in frame, and then we can calculate. But if it would be like below 3, we have to do the second order analysis always. Then the problem is that we have to also include some imperfections in our frame to analyze them correctly. We have many type of imperfections in Eurocode, and they are listed here. So we look closer to all of type of imperfections in the model. So we have like the whole inaccuracy of the building, like the sway deformations. We have an intermediate floor curvature, which is another type of deviation. We have a beam curvature. It can be like example of this top flange curvature, or the column cannot be like perfectly straight. So this is like beam curvature. And then we have a joint curvature. It means that if we have a connection somewhere in the compression element, we should include that one. And this is really common what is missing in models. So joint curvature is like the most common missing type of imperfection in calculation models. And then we have a compressed flange or truss curvature, which is like the example here, and we have a beam internal part curvature, like the deviation of the flanges or webs. And this is taken into account in the cross-section classification. So they are included in the classification table. So you basically, in normal cases, you don't have to take them into account. Do we have a question here or not? What is the spring stiffness you are using for foundations, and how to calculate if it's in, for example, 100 millimeters of gravel? Okay, this is a difficult one, and usually it's missing on the calculation models. But we can ask the tier technique. That is the first option. Then, if we don't have that answer, then we can do some bedding modulus analysis based on the soil type. So there's a different type of soils. They give you different kind of stiffness. So in your case, if it's like 150 millimeters of gravel, it would be like really high a number, 250,000 kilonewtons per per cubic meter is something ballpark estimate. But if you just Google like bedding modulus of subgrade reaction, you get some initial values. And in our software, it's also possible to actually calculate this. The software will calculate it automatically if you put the soils under your foundation. FEM-Design will automatically calculate that what is the bedding modulus you are roughly getting out of your model. So there's a third option. But it's a bit out of the scope of this webinar, so we do not go deeper now. But you can contact us if you want to know these solutions to calculate it with our software. So this is, I will show you with the examples of all of these eccentricities. So this is the floor diagram lateral loads. Then we have these compressed flange curvature. This is actually really complex, and this can be applied to any kind of stiffening system. So if you have like portal frame corners which are under compression, you can use this formula to calculate the supporting loads needed for your steel structures. And the problem is here, I already explained this, but this later, but the problem is here. The QD is the load which will be caused to the lateral bracings by the compressed elements. And it's related to the normal force, like the compression of the flange or compression of upper chord of truss or corner of frame or something. And then we have a E0 and QD. The problem is here that, I mean delta Q. The problem is that delta Q means that it's a deformation of bracing system, including this stiffening force. So this means that this is actually iterative process. So what you have to do is first you calculate this QD, what is like the initial load to the bracing system. Then you look how much it deviates, like, and the problem if you have a connection on your bracing system, they have also have to be taken into account in this. Then you apply this delta Q to this formula, calculate the structure, and again you get larger QD because you have a deformations. Then you do your third iteration and again apply back this QD to the formula and get even larger. And some after like 5 to 2 like iterations, you will end up your final QD, which is like the loading to the bracing system. So that's how you do it. And this is the joint curvature, which is like the most commonly missed type of curvature is in models, because if you have a like connection in this point 1, you have a compression column, compression brace or something, or this can be even like a frame corner or something like portal frame corner. It's really high. 1 divided by 100, which is like really large number. It will give you like really high bracing force needed for your systems. So let's look like this with the example model, how you can put them. There's many options to do them. One option is of course that you use eigenvalue analysis, analyze your buckling modes. But the problem is here that if you use buckling modes to model those initial curvatures, you have to calculate like many hundreds of buckling modes, and usually they are really high buckling modes. So in practical steel structures, it's unfeasible to do it that way. What we can do instead, we can start like with the first diaphragm loads. So for instance, if the stability of this floor is dependent on these columns, we can model it so that we put loads in here in the columns to bend those columns to model those diaphragm loads. So that was the first type of deviation. Then the joint curvature. So let's say that our compression of upper chord is something. We divide it by 100. And then we put load there in the connection, and this will give me some loading to these diagonals to design those connections. The good thing about these joint curvatures that they don't have to be taken into account in the same time as all the other loads. So this is like individual check should be done. So it's Eurocode states that this is like you only have to do these without any other loads. So either it's joint curvature or it's like the truss curvature, but not the both. They are not affecting on the same time. If you do these eccentricities with the loads, the good thing you can also reverse them really easily in the load combinations. So that's why they are so practical. And this is the last example. If this truss wouldn't be like perfectly straight, you have to put this QD load there. And then you calculate the deviations of the trusses or these bracings, taking into account also the connection stiffness, and then you calculate the total QD, and then you have done your iterations and get the final QD. And of course, in here you have to also take into account the wind load affecting same time. Okay, these are the main type of trusses. Then we do our analysis. There's actually like 2 types or even more. I don't go deeply into these, but there's actually many more types in analysis you can actually do according to the Eurocode. But we are just talking about like linear analysis and non-linear analysis. So the deformation of the nodes will give you higher forces. And with the second order analysis, it's important that you put initial deformations in your model. So in our software, there's always option to calculate the imperfections using buckling modes. but you have many other options to do this also. And with the first order analysis, it's important if your alpha critical is below 10, you take into account increase the wind loads in your structure. So this is also one really common missing thing in analysis models. Here you can see the utilization of like columns if you calculate with the linear theory and nonlinear theory. And in this linear theory will correlate really well with the nonlinear theory if you take into account this additional increment of lateral loads like wind loads. You increase your wind load with this factor. So, but eventually when you run the alpha critical will go like low and your structure is really slender, then actually the nonlinear will give you more accurate results. So usually it's so that the nonlinear give you more beneficial results when if the slenderness is low, and if the slenderness is high, the nonlinear eventually will give you higher utilization. And that's why Eurocode has put this limit like 3, that below 3 you should always use nonlinear to calculate your frames. Question, how do you combine these curvatures with your load combinations? I include them always in a load combination, and if you usually put them in the same direction as your wind loads. If you are uncertain, you can do plus and minus. So wind load from the like plus x direction plus the deviation in x direction, and wind load from the minus x direction, and combined with the eccentricities in two directions. Is there any risk of modeling all the connection as pins, or is always on the safe side? It's a tough question because usually it's so that if you put pin connections, it's on the safe side. But in some instances, you get higher stresses to the beams. So according to the Eurocode, it's if they are like semi-rigid connections, they have to be taken into account. So if you have a really stiff connection and the bolts are really tight, then you increase your beam loading by all those imperfections, and that's why it's those semi-rigid connections you should be like avoided, because it's you don't want to go there. But if you have to go then you have to calculate them by this stiffness to get the right result. So pinned is not always on the safe side. Okay, we continue. But if you have any questions, please put them here. Then we have a cross-section classification here if we do it. I just briefly go this, that it's good to understand that cross-section classification, well, this is not about the total stability, but it will only tell you the stability in lengthwise direction of the element. So actually it's things like this, if you have a like thick, like height-wise stresses in your beams, they still can cause like local instability. And also the shear buckling is not taken into account in the cross-section classification. But this is a bit out of the scope of this presentation. Then we go back to the beginning. So like the first dialogue, I show you that there's a question that how you handle your design process in FEM-Design. So you have to select that should we include the second order effects of design of element or not. And this is the Eurocode capital number 5.2.2 sub 0.7 A and B. So the thing is that if we have a like beam model, if it has like all the deviations, it's curved already in the analysis model, and it has a torsional stiffness, so it can torsional buckle. You don't have to do them if you have put them in your analysis model, but you should include like torsional deformations and also like bow imperfections to your model to actually skip these checks. So it's a really important that you understand that if you really do even the element design in your model, global model, then you should have these deformations in your model. And usually the case it's that it's so difficult to do that in practice it's better to do it other way. We check this with the example. So we go back to our model. So let's check that. First we check our alpha critical, it was 5. So it means that we have to increase the wind loads. So we go to the load combination and increase the wind loads for our model to calculate this sway effects correctly. Okay. Then we have get bit higher internal forces. And let's imagine we are designing like these braces in the last bay of this frame, this last frame in the axis number 5. So we go to the steel design, and we want to design this element. And then we have this option. If we do steel design in our software, we have a calculation parameters, and it's this text. Consider second order analysis if available, and it's here. So this is the confusing dialog. So what this means? Ignore second order analysis. It means that it's taken into account only the first order internal forces. Like if you have like a wind load from the side here, it only take into account only the wind load for the first order combination. So this is not good, because we want to have that higher internal forces to this brace because of the additional sway modes. So that is not the right option. Then we have a second option, consider second order analysis if available. So this means that this will analyze this beam with the second order effects. But now we don't have any bow imperfections in the model in this element. So it actually means if I check this element here, if I go and check this one, the utilization is not right because I don't have bow imperfection in this element in the analysis model. So that is not correct either. What we actually want is the third one. We want to have this one. So it may takes the second order global forces, like this one frame in the middle of building will sway to the right side. The second order effects will kick in because the alpha critical is so low. So we want all those additional forces to this brace, what the second order effects are giving us. We can do the global analysis by linear analysis, by increasing the wind loads, or by second order analysis. But anyway, we need those additional loads. Let's assume that we have done our statics with the second order analysis with the global buckling mode as an initial deformation. Then we can do this, that okay, we still do the buckling checks because we haven't included the bow imperfections. So that is the thing why the software will ask you, do we design this element with the global second order forces, but do we still do the local buckling checks with the first order design? So that is the right option for this element. So we cannot skip this part of the process because we don't have those initial deformations in our model. And this is the actual like the captions in Eurocode. So I don't read it now to you. You can check this later. I can send the PowerPoint. But anyway, it just says that you should know that what initial deformations are included in the model and what are not included. Then just a few points about the essential parts of the stability or capacity check if you calculate the capacity, because the alpha critical is not like the total capacity. There's no bending, there's no initial curvature, and the element has like unlimited yield capacity. So these are the most common things are missing. So you need something like a buckling curves to calculate the actual capacity. But I don't want to go these. And then the last part, what you need in good capacity check is the interaction of the bending, which is also not taken into account. It's only taken into account by the Eurocode interaction formulas in Annex A or B with the K factors like here, KY and KYZ. Okay, we have a question. It would be nice if the StruSoft would make a good example of simple case with the step-by-step instruction to how to do this stability calculation in all necessary imperfections meant by calculated correctly. Yes, that would be nice. We might want to even consider that and maybe send it you after this, because this, as you noticed, it's impossible to handle automatically by software. You have to, as a user, you have to understand what are the initial deformations and what need to be taken into account and what kind of analysis process. So it's almost impossible to automate it perfectly. But yeah, absolutely, we can do that one. Hello. Will you put the webinar somewhere so I can review it again? Absolutely, we will put it. And if you have registered in this webinar, you will get the link to the recorded version automatically. So you can watch them with the slow motion. You can even stop it if you want. And of course, you can send it to your friends if possible, if you want to share this webinar. Then a few words about the vibration checks. I think it's usually many cases it's forgotten, but if you have any like long spans, you should consider it, or really lightweight floors or residential office building or something that require good acoustics. sensitive equipment in industry, sometimes you have those. Cantilevers, I would do it every time because they are really sensitive to vibrations. Stairs and then of course like gyms and concert halls, they are steel frames. And this is the approximation of vibrations. So you just take the dead load deformation. And why this formula works is because it takes into account all the same essential stuff as actual vibration check. So you have a stiffness and you have like a loading. Loading is taken into account by this delta, which is deformation. So we get like 4.2 hertz as a vibration mode, and with the exact vibration mode. So it's 4.6 hertz is actual result out of our analysis model. So it's a really close. It's a good approximation. So I would thank you. This was really complex topic, and it was just an overview. We didn't go any details. It was just to give you some ideas what you can have to be taken into account in the analysis. So do you have any other questions? We have some question here. What is the latest question? There's so many. We will check this after the webinar if there's any like question unanswered. But what if we consider the limit 0.7 instead of 1? Can we neglect the second order effects? I don't know what is the limit 0.7. What do you mean by this? So maybe we can discuss after the webinar this. What about torsional buckling effect? Torsional buckling effects, it's always included in our software. If you do steel design manually automatically with our software, it will automatically do torsional buckling check. But what torsional buckling in the 3D models, it's really complex. If you think that the global model will handle those torsional bucklings correctly, you need that torsional initial deformation in the mid of your compressed column, and it's I wouldn't do it in like global model. It's too complex. It's easier just to do it with the automatic Eurocode check of Eurocode. If you get rotation as your first global buckling mode, is that a problem? Well, it's a problem if it's below like 10 or 15. Then you have to take that into account as an initial deformation. And it's actually stated in the Eurocode, if you look at the beginning chapters of the Eurocode 3, that also the rotational buckling modes have to be taken into account. So if you want to do the second order analysis, you have to do it so that you start with those rotational deformations. Put that as an initial deformation. Or if you want to do that lateral load increment, it's really difficult to do then, because then you have to put the lateral loads in your building in opposite ends of building in opposite directions. So it also the hand calculation of first order analysis becomes really complex with the rotational buckling modes. Is this approach applicable to the wooden trusses as well? Of course, but if you look, like if you're talking about, this is Erik who is asking this. Is it applicable to the wooden trusses? Yes, it's applicable, but if you look at Eurocode 5, which is a timber Eurocode, there's a different chapter there how you calculate the initial deformations for timber trusses. So it's a different formula, but basically the formula is same, but the initial deformations are a bit different. So it's you should check your timber Eurocode what it states about those initial deformations of wooden trusses. So it will give you like similar results, and it's the same formula, but the initial deformation in the formula is a bit different. But otherwise, you can do your iteration and hold the other process same way. What is the approach to the model steel beams under the concrete floors, and how you get right distribution of forces to the beam and the floors? Usually the concrete floor takes too much of the forces, and the beam takes too little. It depends what kind of floor do you have. If you have like a one directional floor, like hollow cores, it's important that I can go back to the model and see what this has been done in this model. So for instance here, this is not we have two models for hollow cores in our software. So if you use this one, which has hinges on like in the cross direction, it will give you really low stiffness in the other direction. So actually this beam is the only load-bearing element in this model if you put those hinges between your hollow core slabs. So that is actually a really good model. The other good option is to use those claddings, because they don't have any stiffness. If you have any doubt that you are producing too much stiffness of your concrete floors, then why don't model with the claddings in the vibration analysis or something else? But the hinges will give you almost like the right distribution of stiffness. In continuous column, is the stiffness of the upper and lower elements taken into account in the member buckling design? Oh. Of course, it has to be taken into account. I don't perfectly understand your question, Dmitry, but we can take it after the webinars. I can answer the email to you. Like, think about it this really, and then answer. Can you show the alpha critical requirements bigger than 10 and bigger than 15? Other above 3. Of course, we can go back to this one. It's listed here. No, it was a bit before maybe. So many slides, it's difficult to find. Here, yeah. So first you calculate your alpha critical. If it's go above 10, it means that you can use your elastic. Sorry, if you calculate your capacity of your columns and beams, like your main frame columns with the elastic theory, it has to be over 10. But if you're using plastic calculation, if you calculate your column with like the plastic bending capacity, the problem is that it will go unlinear much easier. The total capacity, if you utilize the plastic capacity, is like 30% higher than the elastic capacity. That's why Eurocode requires you, if you're using plastic capacity of the columns, your alpha critical actually have to be above 15. But if you calculate your capacity with the elastic theory, you can go even to the 10 without any increment of the first order bending moments. And if you go below, like you have like a plastic capacity and like you have alpha critical like 12, you can use anyways this factor to increase like 5% extra wind load to take into account the second order effects. Okay. Is there any more questions? Is the alpha critical only for steel? Yes and no. The stability in timber is handled a little bit differently. You calculate, but basically the same ideology will apply there. And also for concrete, you have like this nominal stiffness method where you increase your loads a bit like this alpha critical increment factor. I don't want to go. There's many questions about timber, so I don't want to go with this supposed to be like a steel webinar. I think that was all the questions. If there's no more questions, we can end for this day. But please, if you're interested in our software or our services, you can always download the trial here and contact us if you're interested. I have to thank you all because it was a pleasure that you have so many questions. I will check all the questions also afterwards and go them through with the Isaac that we didn't left anything unanswered. And if you have any questions about the topics, we can do webinars in future. Please send us. Thank you all for participating and hope you see you soon.